So section 2.4 is going to talk about proving continuity at a point, and we're going to do that using epsilons and deltas. It's a very formal way to show that a point is continuous. And to help you understand this, let's actually look at a problem. It's problem number 20. We want the limit as x approaches 10 of 3 minus 4/5 x. That's going to be some number. Let's see if we can't figure it out. So, what would... It's not that easy yet. All right. Well, can anyone tell me what this limit would be? What's going to happen? How would you evaluate this limit on an exam? Plug it in, right? I mean, that's the first and easiest thing to try when you're working with limit. You plug it in. That's a 10. The 5 and the 10 are going to cancel, so you have 3 minus 8, which would be negative 5. All right, so that's our limit. But let me put this in the context of the epsilons and deltas that we're going to have to work with. So what this is saying is that A is 10. That's the limit of where things are going. This is your function, f of x, and this is L. So in order to show this is a limit, what we want to do is we want to find a value of delta that guarantees that this will be true. Well, let's start by seeing what all this stuff is. So I want x minus 10 to be less than delta, and that should imply that f of x minus L, so it's going to be 3 minus 4/5 x minus negative 5. So minus negative 5, let's put that in here. I want that to be less than some value of epsilon. So basically, what I'm saying is that I want to get really close to my limit. I want to guarantee that, my input, my x values, give me something within this tolerance, my y values. That's what's going on here. And so if I do things right, I'm going to arrange things so that I can get this inequality derived from this inequality. And when I do that, it's going to tell me the choice of delta I use for any particular value of epsilon. And so we'll look at this in a couple examples. And we're just going to do the very simplest cases, which would be the linear case. And I'll try and show you graphically using decimals what's going on as well. But right now, let's do the mechanics of this stuff. I'm going to work with this until I make it look like this. And when I do, I'm going to declare victory and go home. So, first things first, let's take a look at this one. 3 minus 4/5 x minus negative 5 was less than epsilon. There's some simplification I can do in here, right? What's going to simplify in here? Minus negative 5 becomes a plus 5. Plus 5 and 3 gives me 8. Okay. Now, eventually my goal is I want to make this look kind of like this. All right? That's what I want. I want to get that x minus 10 on the left-hand side. So let me change things around, at least in terms of the order on the inside. And to do that, I'll factor out a negative. So it's a negative of 4/5 x minus 8 is less than epsilon. Okay. Getting better. But let me keep going. Overall, what I need here is an x minus 10. So, in particular, the coefficient of x needs to be a 1. So, in addition to factoring out that negative, to rearrange things, I'm going to factor out the 4/5. So, we'll do minus 4/5 times x minus, well, 4/5 is 0.8 as a decimal. What do you get when you divide 8 by 0.8? 10. Okay. Now here's what we'll do. This is a product, and my properties of absolute values allow me to do this. It allows me to factor that out and turn it into the product of two absolute values. Nothing wrong with what I did. This is a Calc 1 class, so I'm sure you can help me out with this one. Absolute value here, 4/5. Thank you. All right. You proved me right. I appreciate that. Now I'm almost there. Remember, my goal was to get this part right here. So I need to get this x minus 10 term by itself. So how would I do that? What could I do to get the x minus 10 an absolute value by itself? Yeah, multiply both sides by the reciprocal. So I get the absolute value of x minus 10. 4/5 times 5/4 is going to cancel here. We're going to have less than 5/4 epsilon over here. And wow, we pretty much declare victory because this is what I wanted. I wanted to figure out how my choice of delta was going to relate to my choice of epsilon. And this is what it is. So let's take a look at what I can do overall. So overall, what I'm going to do is choose delta equal to 5/4 epsilon to show the limit as x approaches 10 of 3 minus 4/5 x equals -5. Why does that do all my work for me? Basically, I'm letting this be my delta. Well, it's because we can work all this backwards. If this is true, then this is true, then this is true, and this is true, this is true, this is true, and then this is true. Basically, once this is true, I can work my way all the way back here. So with this choice of delta, I can find my choice of epsilon. I can get as close as I want in the y-axis based on my choice for the x-axis. So that's the proof. Now what does that mean? What is that saying graphically? Let's go over that graphically. And to do that, you can take a look at that link that I sent you for Desmos, or at least I posted online. I'm going to change our function to match what we have currently. So let's see, there's going to be 3 minus, we'll just call it 0.8x. And I want to look at the limit as x approaches 10. All right, so let's choose ourselves kind of a friendly value for epsilon. Epsilon is how close we want to be to our limit in the y direction. So basically, I'm giving myself a pretty generous tolerance. I want to be within 1. So 1 up or 1 down. And you can see the values here, -4 to 6, even though we know that the limit is actually 5. Let me maybe zoom in a little bit here. There. So the limit is 5. We know that. How close do you have to be in the x direction so that we can still be within our tolerance in the y direction? So that's what the delta is. Delta says, okay, I can be wider and wider and wider and still be within 1 of my limit in the y direction. Now, how far can I go? Well, coming back to our work, delta is going to be 5/4 times epsilon. So what's 5/4 of 1? Well, 5/4. Or as a decimal, 1.25. So let me go back here. And now I'm all good until I get up to 1.25. I'm still good. But if I go past that, then I'm no longer within my tolerance in the y direction. So what we developed there for our choice of delta was perfect, because it told us, the most we could do so that we could be within a precise limit of, or precise tolerance in terms of epsilon. If I dial this down to say 0.6, what's 1.5 times 1.5 times 0.6? Be what? 0.8? Oh, somebody check me on that. 1.5 times 0.6. I'm thinking it's 0.8. So, what is it? 0.9? Oh, excuse me, 1.25 times 0.6 should be 0.8. 0.75? Oh, okay. All right, so 0.75. All right, so my math sucks. This is embarrassing, but whatever. So right now, I'm not close enough in the x direction to be as close as I want in the y direction, 0.6. So let me make delta smaller and smaller, so that as my window around x equal 10, let me get closer to that. And right there when I cross 0.75, that's the threshold. That's where I'm close enough in the x direction to guarantee that I'm within my tolerance in the y direction. So for the appropriate choice of delta, you can prove that this limit is true. And that choice would be delta equals 5/4 epsilon. So, okay, we'll do another one like this. But before I get there, any specific questions on the first one? All right. Let's try another one. Problem number 18. So we'll kind of back up a step. Take a look at problem number 18. Limit as x approaches -2 of 3x plus 5. Can anyone tell me what that limit is? What's that limit going to be? Yeah, -1, right? You just plug in the limit, and that's fine. But if you're going to prove that with epsilons and deltas, then we got to take note of a few things. This is your A. That's your f of x. And that's your L. What we want to show is that the absolute value of x minus A is less than delta implies the absolute value of f of x minus L is less than epsilon. Basically, we can get as close as you want to your limit in the y direction as long as we're close as we need to be to this value of A in the x direction. So is the input close to the out, or close enough in the input gives you close enough in the output. Let's put these things in and see what they are, see what it looks like. So it's going to be the absolute value of x minus what? -2, thank you. And that's going to be less than delta. That should imply that f of x, which is 3x minus 5, or excuse me, 3x plus 5, minus L is less than epsilon. And L in this case is -1. This actually gives you your jumping off part. Your starting point is this part right here. So let me bring that over here, and let's do some work with it. So it's the absolute value of 3x plus 5 minus -1 is less than epsilon. This is going to simplify though, right? So minus -1 to the 5 gives you plus 6. Good. Now keep in mind that we're actually headed to absolute value of x plus 2. That's where we want to go. And I can see the light at the end of the tunnel right away. Sean, is there anything I can do here? Factor out a 3. This would be a 2. So that's a 2. My bad. Well, absolute value of 3 is just 3, right? So how do I finish this up? Divide by 3. I get the absolute value of x plus 2 is less than epsilon over 3. Wow, that's it. When I get this right here, then you're done. This is your choice for delta. So with that choice for delta, that is epsilon over 3, then this is true, this is true, this is true, and then this is true. You get that whole sequence of events. All right. So kind of in summation, you'd say choose delta equal epsilon over 3 to show that the limit as x approaches negative 2 of 3x plus 5 equals negative 1. How'd that one look? Okay on that one? Let's take a look at what that means graphically, just to try and help you understand what this is trying to show you. Basically, like I said, it's trying to show you that if you're close enough in the x direction, you should be close as you want in the y direction. So let's pick a value. How close do you want to be in the y direction? Let's pick something, friendly, maybe divisible by 2, for instance, or by 3, for instance. So let me come back here, change our function. F of x is going to be 3x plus 5. So 3x plus 5. And then I want my limit to be at negative, where was it? Negative 2. Yeah, they're negative 2. So I'll dial that all the way down. I got to recenter my graph a little bit. Okay. So let's check it out. If we're going to do epsilon as 0.6, so we want to be within 0.6 in the y direction, so that's this distance here between 0.29 and 1.7, that's a distance of 1.2, or half of it either way is 0.6. If I want to be reasonably close in the y direction, how close do I have to be in the x direction? Well, we just calculated that. Delta should be epsilon divided by 3. So if if epsilon is 0.6, what should I set delta to? 0.2. So as I dial this down, I'm getting closer and closer to x equal negative 2. Let's see, no, excuse me, x equal negative, was my limit negative 2? Yeah, did I get this set? No. I don't think it went, yeah, it didn't go all the way down to negative 2. There we go. All right, so as I get closer and closer to negative 2 in the x direction, I should get close enough to my limit in the y direction. And let's just dial that down. If I dial it down enough, down to 0.2, this should go from red to green. And basically what that's saying is I've finally gotten close enough to things in the x direction so that I'm within my tolerance in the y direction. And that proves the limit. Basically it says you can get as close as you want. You tell me how close you want to get in the y direction, I'll tell you how close you got to be in the x direction. And that proves the continuity at that point, proves the limit at that point. Okay, any comments or thoughts on epsilon and deltas? These are the easy cases. These are the linear cases. when you start dealing with the quadratic cases and other cases, it becomes a lot more fun. But I'll save that for a different class. For now, we'll leave things here.